Welcome to This Explainer. Today, we're diving into the literal mechanics of the universe, how chemical reactions actually work. We spend our entire lives surrounded by physical materials, right? But just underneath the surface, there's this incredibly complex, almost architectural set of rules governing how absolutely everything around us interacts, transforms, and, sustains life. We're going to break down exactly how this core process works, looking closely at the hidden ledger of atoms that keeps our universe in perfect balance.
Okay, let's dive into this. Have you ever actually stopped to think about what's happening on a microscopic level when a brand new shiny iron nail is left outside and just slowly turns into that brittle, flaky, reddish-brown piece of rust? We see the before and the after, but the mechanics of that transformation are completely invisible to the naked eye. What is actually happening to the atoms themselves?
Because that rusting nail, it isn't an isolated event. Our daily lives are just a non-stop series of chemical transformations. Think about it. Milk left out at room temperature during the summer turning sour, grapes fermenting to become wine, or, hey, even just the simple act of food being cooked and then digested right in our own bodies. In all of these situations, the fundamental nature and the actual identity of the initial substance completely change. It's not just a physical change, like ice melting into water. The material itself is fundamentally, chemically altered.
But since we can't just zoom in with our own eyes to see atoms rearranging themselves, how do scientists actually know a chemical reaction has taken place? Well, nature leaves us clues. In fact, there are exactly 4 key visual or physical clues that investigators look for to confirm a reaction has occurred.
If you spot any of these 4 things happening, a chemical reaction is very likely underway. A change in state, a change in color, the evolution or basically the bubbling up of a gas, and a change in temperature. For instance, if you clean a magnesium ribbon and burn it in air, it doesn't just get hot. It literally combusts with this dazzling white flame and changes into a completely new white powder. Or if you drop zinc granules into dilute sulfuric acid, you'll immediately see bubbles of hydrogen gas forming. Plus, if you were to touch the flask, you'd feel a really significant change in temperature. Now, to really understand this core process, we need a standardized way to talk about it. So we use 2 very specific terms to translate these physical observations into written language. The initial substances that undergo the chemical change, like the magnesium and the oxygen in the air we just talked about, those are called the reactants. And the entirely new substance formed during the reaction, that is called the product. Now, we could write this all out as a sentence or even a word equation: magnesium plus oxygen yields magnesium oxide. But let's be honest, word equations are just way too long for busy chemists. To make these equations concise and universally useful, we use chemical formulas. So, magnesium plus oxygen becomes Mg plus O2, pointing an arrow to MgO. It's a highly efficient shorthand that tells us exactly what elements are at play.
So, the crucial point is this universal rule, the law of conservation of mass. Mass can neither be created nor destroyed in a chemical reaction. When atoms undergo a chemical change, they don't just disappear into the ether, and new atoms certainly don't just magically pop into existence. The universe acts like a strict, meticulous accountant. The total mass of the elements in the products absolutely has to equal the total mass of the elements in the reactants. Every single atom must be perfectly accounted for.
All right, let's put this core process of accounting to the test. Here is what we call a skeletal chemical equation for that rusting iron example. Iron, or Fe, reacting with water, H2O, to produce magnetic iron oxide, Fe3O4, and hydrogen gas, H2. Now, it's called a skeletal equation because it shows the chemical formulas, but if you mentally count the atoms with me across that arrow, you're going to notice a really glaring problem.
Now, what's really interesting about this slide is if you look closely at this broken ledger. Comparing our reactants on the left-hand side to our products on the right-hand side, we start with 1 iron atom, but somehow we end up with 3. We start with 1 oxygen atom, but end up with 4. Our hydrogen is balanced at 2 and 2, but the rest is a complete mess. The mass isn't matching up, which means this equation violates the fundamental law of the universe. We have to balance it.
Okay. Let's slow down and walk through exactly how to fix this using what's called the hit and trial method. Step 1 is absolutely vital. Imagine drawing boxes around each chemical formula. You cannot alter the formulas themselves. You can't just change H2O to H2O4 to get more oxygen, because that changes the fundamental substance itself. You can only put numbers in front of the boxes.
Okay, now for step 2. Let's start with a compound that has the maximum number of atoms. Here, that's Fe3O4 on the right, which has 4 oxygen atoms. To get 4 oxygen atoms on the left, we place a coefficient of 4 in front of the water, making it 4H2O. For step 3, we balance the rest. By making it 4H2O, we now have 8 hydrogen atoms on the left, so we place a 4 in front of the H2 on the right to get 8 hydrogen atoms there too. Finally, we have 3 iron atoms on the right, so we just pop a 3 in front of the Fe on the left.
And there we have it, a perfectly balanced chemical equation. The ledger is officially matched. 3 iron atoms on both sides, 8 hydrogen atoms on both sides, and 4 oxygen atoms on both sides. Now, to make this equation a truly complete sentence, we also add physical state symbols. That little S tells us the iron is solid. The G tells us the water is actually in the form of a gas, or steam, in this specific reaction, yielding a solid product and a gaseous hydrogen product.
Let's move to and see how this builds into the different types of chemical reactions, which are essentially variations in the core process. We know how to balance the math on paper, but physically, these reactions happen because chemical bonds are actually breaking and making new connections between atoms. And as you'll see, they tend to follow a few distinct, fascinating patterns.
The first variation is the combination reaction. This is when 2 or more substances combine to form a single, brand new product. Here, calcium oxide, also known as quicklime, is reacting vigorously with water. They combine to form a single product called slaked lime. But what's truly incredible here is that this specific combination is highly exothermic. It releases a massive amount of heat, literally making the beaker hot to the touch.
Conversely, we have the decomposition reaction. This is the exact opposite. Here, a single reactant is broken down into simpler products. Notice how heating green ferrous sulfate crystals in a boiling tube physically forces the single compound to break apart. It loses water, its color changes, and it decomposes into solid ferric oxide while emitting distinct, pungent gases like sulfur dioxide. When heat is used to force this breakdown, we call it thermal decomposition. And this brilliantly illustrates another fascinating way decomposition can happen. Not with heat, but with electricity. By running a current from a 6-volt battery through water containing a few drops of acid, the electrical energy literally tears the H2O molecules apart. The single liquid reactant decomposes into bubbling hydrogen gas at one electrode and oxygen gas at the other. It is a visible mechanical breaking of chemical bonds.
Once you understand this core process, how atoms rearrange themselves, how mass is perfectly conserved, how energy is either absorbed or released, you realize that chemistry isn't just something happening in a beaker in some lab. It's happening inside you. The very act of respiration is an exothermic chemical reaction. The glucose from the food you eat is combining with the oxygen you breathe, breaking down to form carbon dioxide and water, and releasing the exact energy keeping you alive right now as you watch this explainer. The ledger is balancing itself inside your cells, every single second. So, as you go about your day, I want to leave you with this. What else is burning, breaking, and combining in the world around you? Thanks for joining me on this explainer, and keep exploring.